Alright, for our final video here we're going to talk about kinetic friction again, but this time when we have an object that's accelerating. So let's say we have a crate of apples and we need to push this across some sort of belt in order to load it onto a truck. So we push with a force of 50 newtons and the crate accelerates at a rate of 1.1 meters per second squared. The mass of the crate is 30 kilograms. So we need to list our important information. The force of the push we know is 50 newtons. Oh, little too many newtons there. There we go, 50 newtons. The acceleration is 1.1 meters per second squared. So we know that because these units are units for acceleration. And then the mass is 30 kilograms. Okay, so if we draw a free body diagram, we know that the force of the push is this time not going to be balanced by the force of friction because we are accelerating. So the acceleration is going to be in the direction of our push. So that means that the force of friction is going to be smaller than the force of our push. Okay, we know that it's going to accelerate in the direction of our push because that was the premise of the problem, is that we're pushing it in order to get it to move somewhere. So we're assuming that it's starting slow or at rest and we're accelerating it in the same direction as our push. It's possible that the push is less than the force of friction. In that case, the object would be slowing down. But in this case, it's going to speed up in the direction of our push. So we also know there's the force of gravity and the normal force. Okay, so let's say that what we want to find is this force of friction. What is the force of friction? So FFK equals what? So we know we have an equation that involves FFK. It's this, equals mu k times the normal force. Now, in order to solve for FFK, we would need to know the coefficient of friction and the normal force. The normal force we can figure out because we know the mass, and we know that the normal force is equal to the force of gravity. And we can find this because this equals m times g. So the other thing we would need to know would be the coefficient of friction, and we don't know that. Okay, and there's not another equation that we have that has this value in it that we could use to find this. So this equation is not going to be helpful for us to find the force of friction. So we need to figure out some other way. Well, we know that Newton's second law relates acceleration with the net force. And we know all of these forces except for one. So that means we can use Newton's second law to find our one unknown force. So Newton's second law says F net equals m times a. So we're going to replace this generic net force, total force, with the actual forces we have. That would be the force of the push plus the friction force. Now we know the friction force is going to be negative because it's pointing in the opposite direction. So we could even put a little negative there to remind us that that's going to be a negative. That equals m times a. Of course, putting this negative, we're implying that this direction is positive and this direction is negative. So we'll write that up there just in case we need to use that coordinate system for another part of the problem. Okay, so now we know the force of the push, we know the mass, we know the acceleration. So it's just a matter of plugging everything in. Oh, this was 50 newtons. And our mass was 30 kilograms. And our acceleration was 1.1 meters per second squared. So we get our FFK, which we know is going to be negative, works out to be negative 17 newtons. Okay, so this tells us that the negative tells us it's pointing in the negative direction. Okay, so if we cancel these out, that tells us that the magnitude of the friction force is 17 newtons. Okay, so the friction force, FFK, the magnitude of the force would be 17 newtons. That's the size of the force. And according to our picture, we know it points in the negative direction. Now, let's say that the problem asks us to find the coefficient of friction between the crate and the conveyor belt that it was sliding across. How do we go about doing that? Well, we can go back to this equation, where we said this is the only equation that has mu k in it, the coefficient of friction. So in order to solve for this, we need to use this equation. So we would need to know the normal force and the force of friction. Well, we just found the force of friction, so that's good. And the normal force we know is equal to the force of gravity, which we can find if we know the mass. So that's good. So now we can just plug everything in and solve for mu k. So the force of friction was 17 newtons. And the normal force, we know that that's equal to the force of gravity, and that's equal to m times g. So we're going to replace Fn with m times g. So now we have 17 newtons equals mu k times the 30 kilograms times 9.8 meters per second squared. And if we work that out, that gives us mu k equals 0.06. Okay, so that's a very low mu k. That tells us that this is a very slippery surface. There's not much friction between the crate and the conveyor belt. Now, you might come across a problem that asks you to solve for mu k just given this information and doesn't necessarily ask you to find the force of friction first. So you have to know that you would need the force of friction in order to solve for mu k. So you would have to use Newton's second law and find the force of friction through this means so that you can then plug it into this equation and solve for mu k. Alright, let's try one more example. In this example, let's say we have a garbage can and we're pushing it across some grass. We have to drag it through our yard. So our mu k is fairly high because dragging it through grass is going to provide a significant amount of resistance. So let's say that's 0.72. Okay, suppose the mass is 18 kilograms. This time, we want to know if we pull with a force of 140 newtons, what's going to be the acceleration? Okay, so to find the acceleration, we would either need to know some information about the distance moved and the time it took to move the distance and how much the velocity was changing. That was stuff from Chapter 3. We don't know anything about any of those quantities. So instead, the other thing that we just learned that has acceleration in it is Newton's second law. So we're going to use that to find acceleration. So that says F net equals ma. So we know m, and we know one of the forces. So we need to figure out what the other forces are in order to solve for a. So let's say we're pushing this way. That's 140 newtons. Okay, if we want to get this to accelerate, if we're assuming that there is acceleration, then that means our friction force is going to be smaller than that. And then of course we also have the force of gravity balanced by the normal force. Okay, so we only need to look at the x direction for our Newton's second law because we know these y direction forces are going to cancel each other out. So our net force then would be the 140 Newton push plus the force of friction, which we know is going to be negative, so we could put that in to remind us. And that will equal the mass, 18 kilograms, times the acceleration. Now, we're missing something here. To solve for a, we need to know everything else, and we don't know the force of friction. So how can we find that? Well, in the previous problem, we found this force by using this equation. That's not going to work this time because we have another unknown here. So now we have to use our other equation that has FFK in it, which is FFK equals mu k times the normal force. So this time, we know what the mu is. It's 0.72. And the normal force is equal to the force of gravity, which is equal to m times g. So we're going to plug in m times g in place of the normal force. So that leaves us with FFK equals 0.72 times the mass of 18 kilograms times 9.8 meters per second squared. And if we work that out, that gives us about 127 newtons. So at this point we can stop and think, 127 newtons. We can stop and think, does this make sense? Okay, so we know that we want it to accelerate in the direction that we're pushing it. That means our pushing force needs to be bigger than the friction force. So one thing to note is that this friction equation only gives you the magnitude of the force. This doesn't automatically give you the direction. So you need to refer to your diagram. So we know that the direction of this would be in the negative direction. So if this is smaller than our push, that means it's going to accelerate in the direction of our push. So this makes sense. So now that we know the force of friction, we can plug it back in here, remembering to make it negative because it's in the negative direction. So 140 newtons minus 127 newtons for our negative direction equals 18 kilograms times A. Now we have everything we need to know to solve for A, and we get A equals 0.72 meters per second squared. Okay, so does this make sense? Well, first of all, it's positive, so that's good, because that means it's accelerating in the direction that we're pushing. Second of all, it's fairly small. This means that in 1 second, the garbage can would speed up by 0.72 meters per second. And that seems reasonable. It's not super fast. So our answer makes sense. And that's it.